Hey everyone, and welcome back to Key Safety Talks. Today we're going to be diving into something that's super important in any workplace and, even in our homes, ventilation.
Yeah, it's one of those things we don't often think about until, there's a problem.
Exactly. We'll be looking at how to keep the air clean and what you could do to make sure you're breathing easy, especially when you're in environments where there are some potential hazards.
Right.
We're going to be using a safety professional's go-to resource, a well-known reference book, to really help us break down this topic.
And this guide really does a great job of not just, defining ventilation, but explaining why it matters and how to actually do it right.
Yeah, and we're going to be looking at some real-world examples and even doing some calculations together so you can grasp the concepts in a more practical way.
Sounds good.
All right, so before we get into the specifics of ventilation, let's quickly touch on the bigger picture of hazard control. Now, we know there are 5 main methods: elimination, substitution, engineering controls, administrative controls, and personal protective equipment, or PPE for short.
Right. Those are the big 5.
And ventilation falls under which one?
That'd be engineering controls.
Right, because it involves physically changing the environment to reduce those risks.
Exactly. It's about building that safety net right into the workplace itself.
Okay, so let's jump into the world of ventilation now.
All right.
Our trusty guide breaks it down into 3 basic categories: general, dilution, and local exhaust ventilation.
Right. 3 main ways to tackle this.
And I think starting with general ventilation makes sense.
Yeah, think of it like your home's HVA system. That's general ventilation in a nutshell.
So it circulates air to keep everyone comfortable and brings in some fresh air from outside.
Exactly, but it's not really designed to handle specific hazards, things we might find in a workplace.
Right, it's more about overall comfort.
Right.
And then we have dilution ventilation.
This one's kind of like, adding a splash of clean water to a glass that's maybe got a little bit of something in it.
So it's about diluting the concentration.
Exactly. You're mixing fresh air with the contaminated air to bring down that overall concentration of pollutants.
And that works well for situations where the contaminants are spread out and not super toxic.
Right. It's a good option for certain scenarios.
But when you're dealing with something seriously dangerous, you need something a bit more powerful, right?
Right. And that's where local exhaust ventilation comes in.
That's the heavy hitter.
Yeah, think of those fume hoods you see above welding stations. They capture the contaminants right at the source before they have a chance to spread.
Okay, so we have these different types of ventilation, but how does air actually move in a ventilation system?
It all comes down to a fundamental principle. Air flows from high pressure to low pressure.
Like a balloon.
Exactly. When you let go of the opening, all that air rushes out from the high pressure inside to the lower pressure outside. That's basically the driving force behind all types of ventilation, whether it's in your home or a big factory.
So the guide gives us a formula for calculating airflow. Q equals V times A, where Q is the flow rate, V is the velocity of the air, and A is the cross-sectional area of the duct or opening.
Right. That's our basic equation.
And here's something that really surprised me. Even when the air seems perfectly still, there's still some movement.
Yeah, it's constantly moving at around 25 feet per minute.
Wow. So there's always some level of air movement happening, even if we can't feel it.
Right. It's a bit like, those tiny currents you can sometimes see in a seemingly still lake.
Okay, so to really understand how we can control that air movement, we need to talk about a few key concepts: static pressure, velocity pressure, and total pressure.
Yeah, these are the building blocks.
And the guide has a really helpful diagram, figure 7.1, to help us visualize this.
That one's a good visual aid.
So static pressure is kind of like the potential energy of the air. It's the pressure that the air exerts just by existing.
Right, it's like the pressure inside a tire before you even start driving.
Then we have velocity pressure, which is the pressure created by the air's movement. It's kinetic energy.
Right, like the wind you feel when you're riding a bike.
And total pressure is simply the sum of those two.
Static plus velocity equals total pressure.
Easy enough. So how does this all apply to a real-world situation? Like, how does an exhaust fan actually work?
Well, when the fan is running, it creates lower static pressure on one side.
Okay.
And that draws in air from the surrounding area where the pressure is higher, kind of like a vacuum.
It's all about that pressure difference.
Exactly. And here's where it gets really interesting. The velocity of the air plays a huge role in how effectively we can capture and remove those contaminants.
Oh, so the faster the air moves, the better it can carry those contaminants away.
Exactly. It's like If you're trying to sweep up some dust.
If you sweep slowly, the dust just kind of moves around.
Right, but if you sweep quickly, you can actually lift that dust off the floor and into the dustpan.
Perfect analogy. And we'll see this principle in action later when we talk about local exhaust ventilation, especially this concept of capture velocity.
That's a key concept for sure.
Okay, so now that we have a basic understanding of how air moves, let's talk about how we actually use ventilation to control those hazardous substances in the air.
Right, let's get practical.
So the guide really emphasizes the importance of calculating how much of a contaminant is being generated in the first place.
Yeah, that's step one.
Because that helps us design a ventilation system that's powerful enough to remove it.
Right, you need to know how much you're dealing with.
It's like knowing how much water is leaking from a faucet so you can choose the right size bucket to catch it.
Exactly. And the guide actually walks us through an example using acetone.
Acetone. Like nail polish remover.
Yeah, it's a common solvent used in all sorts of industries.
Okay.
So imagine you're working with acetone in a confined space. If you don't have adequate ventilation, those fumes can build up really quickly.
And that could be dangerous.
Very dangerous. So that's where this concept of purge rate comes in.
Purge rate.
Yeah, it tells us how long it takes to bring the concentration of that contaminant down to a safe level after the source is removed.
Oh, so like airing out a room after you've been painting.
Exactly. The guide uses an example to show how the concentration of a contaminant decreases over time with proper ventilation.
It's important to remember that even after you stop working with something hazardous, it still takes time for the air to fully clear out.
Yeah, that's a key point because inadequate ventilation can actually lead to a buildup of contaminants over time.
Like a slow leak that eventually fills a room with water.
Exactly. You might not notice it at first, but the damage can be significant over time.
Okay, so we've talked about general and dilution ventilation.
Right.
Now let's dive deeper into local exhaust ventilation, which is that real workhorse when it comes to controlling those highly toxic substances right at the source.
All right, let's get into the nitty-gritty.
It's kind of like a specialized vacuum cleaner designed to suck up those harmful fumes and dusts before they can reach you.
Yeah, that's a good way to think about it.
The guide uses a welding station as an example.
That's a classic example.
So picture this. You have a hood positioned right above the welding area,
Right.
capturing those fumes as they're generated.
Keeping them contained.
Then a duct carries those fumes away to a fan, which pulls air through the entire system and ultimately exhausts those contaminants safely outside.
It's a whole system working together.
And the guide actually breaks this system down into its 5 key components: the hood, the duct, the fan, the air cleaning device, and the exhaust stack.
5 essential pieces to the puzzle.
So starting with the hood, it seems pretty straightforward, but there's actually a lot more to it than meets the eye, right?
Oh, absolutely. There's a whole science to designing a hood that effectively captures those contaminants.
Okay, so what are some of the things we need to consider?
Well, one important concept is hood entry loss. Basically, it's the energy that's lost as air moves from the surrounding area into the hood opening.
I wouldn't have thought about that.
Yeah, it's kind of like trying to pour water from a pitcher with a narrow spout. Some of the water is going to spill and splash because of that restricted flow.
So the more abrupt the change in airflow direction and the smaller the hood opening, the greater that energy loss will be.
Exactly. And that makes the system less efficient because the fan has to work harder to make up for that energy loss.
So how do we make the system more efficient?
Well, one way is to design the hood to have a smooth, gradual transition from the surrounding air into the hood opening.
So minimize that turbulence.
Exactly. Some hoods even have flared openings or flanges to help streamline the airflow.
So it's like designing a well-engineered on-ramp for a highway. You want a smooth, gradual merge to keep the traffic flowing smoothly.
Perfect analogy. And remember, reducing hood entry loss means the fan doesn't have to work as hard, saving energy and money.
And now let's talk about capture velocity again.
Right, that's a key concept.
So how do we actually calculate capture velocity?
Well, the guide gives us an equation for calculating capture velocity for open hoods.
Open hoods meaning?
Hoods that aren't enclosed, like you might see over a welding station.
Gotcha.
The equation takes into account the airflow rate, the distance from the hood opening to the source of contamination, and the size of the opening.
Okay, so the closer the hood is to the source, the lower the required capture velocity.
Exactly. It's like using a small vacuum cleaner for a tiny spill versus needing a shop vac for a big mess.
Makes sense. The guide also gives us an example calculation using a round hood, showing us how to determine the area of the hood opening and then plug those values into the equation.
It's always good to see how those equations work in practice.
All right, so once those contaminants are captured by the hood, they travel through the ducts.
Right, the ductwork is like the highway system for those contaminants.
So what are some of the key considerations when it comes to duct design?
Well, one of the most important is duct size.
Makes sense.
If the duct is too small, it creates a lot of resistance to airflow.
Like trying to force a river through a straw.
Exactly. And that makes the fan work harder and could reduce the effectiveness of the whole system.
And what if the duct is too big? Is that a problem too?
It can be.
How so?
Well, if the air velocity is too low, it can allow contaminants to settle out and accumulate inside the ductwork.
So you don't want it too small or too big.
Exactly. You need to find that sweet spot, the right duct size for the specific application.
Okay, and then there's duct branching too, right?
Right. When a single duct splits into multiple branches, you need to make sure the airflow is balanced.
So that all the branches are getting the right amount of air.
Exactly. Otherwise, some branches might get overloaded with contaminants while others aren't doing their job.
And the guide gives us a simple equation for calculating airflow in ducts.
Based on the velocity and the cross-sectional area.
Okay, so now we've captured the contaminants with the hood, and we're transporting them away with the ducts. But how do we create the force that moves the air through this entire system?
That's where the fans come in.
The fans are like the heart of the system.
They provide the energy to move the air and create those pressure differences.
And we know air flows from high pressure to low pressure.
Exactly. That's the driving force.
We talked about the two main types of fans earlier, axial and centrifugal.
Right?
Can you remind us how they actually work?
Sure. Imagine an axial fan like a propeller on an airplane.
Okay.
The blades rotate around a central axis, pushing air in a straight line.
Simple and efficient.
Exactly. And they're great for general ventilation where you need to move a lot of air, but don't need to overcome much resistance.
Like those big ceiling fans you see in warehouses.
Exactly. Now, centrifugal fans work a bit differently.
Okay, how so?
Well, they have a spinning impeller with curved blades that draw air in and then fling it outwards at a 90-degree angle.
So the air enters axially and then exits radially.
Exactly. And this design allows centrifugal fans to generate higher pressure, making them ideal for systems with more resistance, like those with long duct runs and lots of bends.
So they're kind of like the heavy-duty pumps of the ventilation world.
A good way to think about it.
But how do engineers know what kind of fan to use for a specific system?
Well, they use calculations to determine the static pressure across the fan, which is the difference in pressure between the inlet and the outlet.
So the fan needs to be powerful enough to overcome that pressure difference and maintain the desired airflow.
Exactly. And the guide gives us an equation for calculating static pressure, taking into account the pressure at the fan outlet and the velocity pressure at the inlet.
Okay, so it all ties back to those fundamental principles of air movement.
It all comes together.
Now, we've talked about moving the air, capturing those contaminants, and transporting them away. But what happens to those contaminants once they're removed?
That's where air cleaning devices come in.
Air cleaning devices.
Yeah, they remove the contaminants from the airstream, making sure that the air being exhausted or recirculated is clean and safe.
So they're kind of like the filters in your car or your home's HVAC system.
Right, except they're often much more specialized and powerful.
Okay, so what are some of the different types of air cleaning devices?
Well, we have filters, scrubbers, and electrostatic precipitators.
And they each work in different ways.
Exactly. Each one uses a different method to remove contaminants depending on the type of contaminant and the level of purity you're trying to achieve.
All right, so how about filters? How do those work?
Filters use a porous material like fabric or paper to trap particles from the airstream.
Kind of like a sieve.
Exactly. And the efficiency of a filter depends on the size of those pores and the type of material used.
So some filters remove large particles like dust.
Right, while others are designed to capture much smaller particles like bacteria and viruses.
It's amazing how much science goes into something as seemingly simple as a filter.
Yeah, there's a lot of technology behind it.
Okay, what about scrubbers?
Scrubbers use liquid to remove contaminants from the air.
So it's like washing the air.
Exactly. The contaminated air passes through a chamber where it comes into contact with a scrubbing liquid, and the contaminants either dissolve in the liquid or are physically captured by it.
So scrubbers are good for removing things like gaseous contaminants and odors.
Yeah, they're good for a variety of applications.
Okay. And lastly, what about electrostatic precipitators? Those sound pretty high tech.
They are. They use static electricity to remove particles from the air.
Static electricity.
Yeah, they charge the particles and then attract them to oppositely charged plates, where they collect and can be removed.
Wow, that's pretty ingenious.
It is, and this method is very effective at removing fine particles like smoke and fumes.
So it's like a magnet for those tiny particles.
Exactly. And as you can see, each air cleaning device has its own strengths and weaknesses, so choosing the right one depends on the specific situation.
All right, so we've covered a lot of ground in this first part of our discussion on ventilation.
We have. It's been a good overview.
We've talked about the different types of ventilation systems, the components of local exhaust systems, the importance of air cleaning devices, and even the tools used to measure and monitor these systems.
Yeah, we've hit a lot of key points.
And one thing's for sure, ventilation is a complex but absolutely essential part of maintaining a safe and healthy work environment.
Absolutely. And we've just scratched the surface. There's so much more to learn about this fascinating field.
Well, we'll be right back after a short break.
Looking forward to it. So, welcome back to Key Safety Talks. And before the break, we were talking about all the different components of local exhaust ventilation systems and how those are so important, for keeping the air clean and safe in workplaces. Now, let's dig a little deeper into a concept we talked about a bit earlier, that hood entry loss.
Yeah, you mentioned that hood entry loss is the energy that's lost when air moves from the surrounding area into the hood. Why exactly does this happen? It seems like it should just, flow right in.
Well, it's not quite that simple. You have to picture the air as it's approaching that hood opening. As it gets closer and closer, it has to squeeze through a smaller and smaller space, which creates friction and turbulence.
Oh, okay.
And just like when you rub your hands together, it generates heat. That turbulence dissipates energy, which makes the whole system less efficient.
I get it. It's like trying to get a crowd of people through a single narrow doorway.
Exactly.
There's going to be a lot of pushing and shoving,
All right.
and it's going to take a lot longer than if there were, multiple doorways or a wider entrance.
That's a great analogy. And, the more abrupt that change in airflow direction is, and the smaller the hood opening, the greater that energy loss will be. But luckily, engineers have figured out ways to minimize this.
Oh, that's good. So how do they make the system more efficient? Do they just make bigger hoods?
Not necessarily. Sometimes bigger isn't better. It's more about designing the hood in a way that creates a smooth, gradual transition from the surrounding air into the hood opening. And this minimizes that turbulence and reduces that energy loss. Some hoods even have flared openings or flanges, to help streamline that airflow.
Oh, okay, I see.
Yeah. It's like designing a really well-engineered on-ramp for a highway.
Makes sense.
You want a smooth, gradual merge to keep that traffic flowing smoothly.
Right, yeah.
Exactly. And remember, the less hood entry loss you have means the fan doesn't have to work as hard to move the same amount of air, which saves energy and ultimately saves money, too.
Now, let's get back to capture velocity. We talked about that earlier, and it seems like a pretty straightforward concept, but how is it actually calculated?
Well, the guide, it gives us a helpful equation for calculating capture velocity, specifically for open hoods.
Open hoods?
Yeah, hoods that aren't enclosed.
Okay.
Like the ones you might see over a welding station or something like that. And the equation takes into account the airflow rate, the distance from the hood opening to the source of the contamination, and also the size of the opening. What's interesting is that the closer the hood is to the source of the contamination, the lower the required capture velocity is.
Oh, that makes sense.
Yeah.
Yeah, because if the hood is right next to the source, you don't need as much force to pull those contaminants in.
Right.
It's like using a small handheld vacuum cleaner for a tiny spill versus needing like a big shop vac for a huge mess.
Exactly. And the guide walks us through an example calculation for this.
Oh, good.
Using a round hood, showing how to determine the area of that hood opening and then plugging those values into the equation to determine the capture velocity.
So it's really all about making sure the air is moving fast enough at that hood opening to really catch all those contaminants.
And overcome any of those competing air currents, right?
Right.
Yeah.
Exactly.
Yep.
Okay. Now, once the contaminants are captured, they travel through the ducts, right?
Right.
Are there specific considerations when it comes to duct design? I mean, I imagine you don't just slap any old pipe up there.
No, you're absolutely right. Ductwork is super important, and if it's not designed well, it can lead to inefficiencies and sometimes even safety hazards.
Oh, wow.
So one key thing to think about is duct size.
Okay.
Because if the duct is too small, it's like, trying to force a river through a straw.
Yeah.
It creates so much resistance, it makes that fan work way harder, and could even reduce the effectiveness of the entire system.
Okay. Now, what happens if the duct is too big? Is that a problem?
Yes, it can be. If the duct is too large, then you end up with low air velocity, which can allow contaminants to settle and build up inside the ductwork.
It's like having a slow-moving river where sediment can build up over time.
Exactly.
So it's really all about finding that sweet spot.
The Goldilocks zone.
Yeah, right. Too small, you restrict the airflow, but too big, and you risk, contaminant buildup.
Exactly. And we can't forget about duct branching either.
Duct branch?
Yeah, when a single duct splits off into, multiple branches.
Okay.
It's like dividing a river into smaller streams, right?
Right.
You need to make sure that the airflow is balanced so that all the branches are getting the right amount of air. Otherwise, some branches might get overloaded with contaminants while others aren't doing their job.
The guide, it provides a simple equation for calculating airflow in those ducts.
Based on velocity and cross-sectional area.
Okay, so now we've captured the contaminants with the hood. We're transporting them away with the ducts. How do we actually create the force that moves the air through the whole system?
Well, that's where the fans come in, right?
Right. Fans are like the muscles of the operation.
Yeah, they're the workhorses that provide the energy to move the air and create those pressure differentials.
And we know air flows from high pressure to low pressure.
Right. Always.
So we talked earlier about the two main types of fans.
Yeah.
Axial and centrifugal.
Right.
Can you just remind us how they actually generate that airflow?
Sure. So picture an axial fan. It's kind of like a propeller on a boat.
Okay.
The blades rotate around a central axis, just pushing the air in a straight line.
Okay.
And this design is super simple, it's efficient, and it's great for general ventilation when you just need to move a lot of air, but you don't have to overcome a lot of resistance.
So for situations where you're not fighting against, lots of twists and turns in the ductwork.
Exactly. Now, centrifugal fans, they work a little differently. They're more like a water pump.
Okay.
They have a spinning impeller with curved blades, and it draws that air in axially and then forces it outwards radially.
So the air enters along the axis, and then it exits at a 90-degree angle.
You got it. And this design, this allows centrifugal fans to generate much higher pressure, which makes them ideal for systems where there's more resistance to airflow.
Oh, okay. So like duct systems with lots of bends and branches.
Right, exactly.
It's interesting how the different fan designs, are suited for such different purposes.
Yeah, each one has its strength.
But how do engineers figure out which type of fan to use for a specific ventilation system?
Well, it all comes down to calculations.
Oh, of course.
You have to determine the static pressure across the fan,
Which is?
the difference in pressure between the inlet and the outlet,
Okay.
and the fan has to be powerful enough to overcome that pressure difference and keep that desired airflow rate going.
So it needs enough muscle to push all that air through the system.
Right. And the guide gives us an equation for calculating the static pressure, and it takes into account the static pressure at the outlet and the velocity pressure at the inlet.
Okay, so it all comes back to those basic principles of air movement we talked about before.
It always does.
Now, we've captured the contaminants, we're moving them away. But what happens to those contaminants once they're actually removed from the work area?
That's where air cleaning devices come in.
Air cleaning devices. What are those?
Well, they're these devices that are designed to actually remove those contaminants from the airstream, ensuring that the air that's being exhausted or recirculated is clean and safe.
Oh, so they're like the filters in our cars.
Exactly, or like the filters in your home HVAC system.
Right.
Except they're often much more specialized and powerful.
Oh, wow.
Yeah. So we have filters, scrubbers, and electrostatic precipitators.
And each of those works in a different way, right?
Exactly. Each one uses a different method for removing contaminants, and it depends on, what type of contaminant you're dealing with and the level of purity you need.
Okay. Let's start with filters. How do those work?
So filters, they use a porous material. It could be fabric, paper, mesh, to trap those particles from the airstream.
Like a sieve?
Yeah. And the efficiency of the filter, that depends on the size of those pores and the type of material being used.
So some filters will remove large particles like dust and lint, and others are made to capture much smaller particles like, bacteria or even viruses.
Exactly. There's a whole range of filters out there.
It's amazing how much science and technology goes into something as seemingly simple as a filter.
It is. It's a whole field of study.
Okay, so what about scrubbers? How do those work?
Scrubbers use a liquid to remove those contaminants from the air.
So it's like washing the air?
Yeah. The contaminated air passes through a chamber, and in that chamber, it comes into contact with a scrubbing liquid, and those contaminants either dissolve into the liquid or are physically trapped by it.
Oh.
Scrubbers are really effective for removing things like gaseous contaminants and odors.
So if you're dealing with, something that smells really bad, a scrubber might be the way to go.
Exactly. And then finally, we have electrostatic precipitators, which are pretty high-tech.
Yeah, that sounds fancy.
They use static electricity to remove particles from the air.
Static electricity, like when you rub a balloon on your hair?
Kinda. So they charge the particles, and then they attract them to oppositely charged plates, where they collect and can be removed. This method is really efficient for removing fine particles like, smoke and fumes.
So it's basically like a magnet for those tiny particles.
Yeah, good way to think about it.
It's amazing how many different techniques there are for cleaning the air.
It is. Engineers have a whole toolbox of solutions.
Okay, so now let's switch gears a bit and talk about those instruments used to measure and monitor ventilation systems.
Right.
We talked about pitot tubes, rotating vane anemometers, and thermal anemometers earlier.
Right, the essential tools of the trade.
Can you elaborate on how they're actually used and why they're so important?
Sure. So pitot tubes, those are simple devices, but they're used to measure velocity pressure.
Okay.
They're basically tubes with a small opening that faces the airflow.
Okay.
And by measuring that pressure difference between the air entering the tube and the static pressure of the surrounding air, we can figure out the velocity pressure, which tells us how fast the air is moving.
It's like a speedometer for air.
Exactly. Now, rotating vane anemometers, they use a small propeller, or a vane, that spins when it's exposed to airflow. And the speed of the rotation is directly proportional to the air velocity, so it's kind of like a tiny windmill telling us how much air is flowing.
That's pretty cool.
It is. And lastly, we have thermal anemometers, which use a heated sensor to measure air velocity. So as air flows past the sensor, it cools it down.
Okay.
And that rate of cooling, that's proportional to the air velocity. Thermal anemometers are particularly useful for measuring really low air velocities and turbulent flows.
So we have these different instruments to measure airspeed, air volume, and even air turbulence.
Right. We need to measure it all.
But why is it so important to monitor all these aspects of ventilation systems?
Because ventilation systems don't just operate in a vacuum, right?
Right.
They're affected by all sorts of things. Changes in production processes, equipment wear and tear, even weather conditions can play a role.
So it's like regularly checking the tire pressure in your car.
Exactly. You might not notice a slow leak, but over time that can lead to a flat tire, right?
Right, yeah. Big head.
Exactly. By monitoring our ventilation systems, we can catch those potential problems early and prevent issues that could really put workers' health and safety at risk.
Okay, so we've really delved deeper into the world of ventilation here.
I have.
Exploring, all the details of hood entry loss, capture velocity calculations, and the importance of duct design.
It's been a good discussion.
We even talked about how those different fans create airflow and the technology behind air cleaning devices and the instruments that are used to measure and monitor these systems.
It's a fascinating field.
Absolutely. And it's clear that ventilation is a very complex field.
With a lot of moving parts.
But it's absolutely crucial for keeping workplaces safe and healthy.
It's essential.
Now, in the final part of our discussion, we're going to explore some of the calculations that safety professionals use to really assess and design these systems.
That's where it gets really interesting.
And we're also going to look at some exciting innovations that are shaping the future of ventilation technology, so stay tuned.
I'm excited for that.
And we're back with Key Safety Talks. Feeling pretty pumped after our deep dive into ventilation so far. We've gone from the basics of how air moves all the way to the nitty-gritty details of those local exhaust systems.
It's been quite a journey, and now we're going to shift gears just a bit and tackle some of those calculations that safety professionals actually use out in the field to, design and assess these systems. I know math can be a little intimidating, but trust me, these calculations, they're super important for making sure that ventilation systems are doing their job, keeping workers healthy and safe.
I'm ready. Hit me with some of those equations.
Okay, so a really common calculation that you'll see is figuring out the number of air changes per hour in a room.
Air changes per hour. What's that?
So basically it tells you how many times the entire volume of air in that room is replaced with fresh air every hour.
Oh, okay.
It's a simple metric, but it's super useful for assessing general ventilation.
So how do we actually calculate that? Do we need a fancy calculator?
Nope, not at all. The guide gives us a nice straightforward equation
Okay.
that uses the ventilation rate and the volume of the room. Think of it like, figuring out how many times you can fill up a bathtub using a certain size bucket.
Okay, I can visualize that.
Yeah. So for example, if we know the ventilation rate is 2,500 cubic feet per minute,
Okay.
and the room volume is 75,000 cubic feet, we can easily calculate the number of air changes per hour.
It seems pretty straightforward, yeah.
Yeah.
And it makes sense that a bigger room would need a higher ventilation rate to achieve the same number of air changes as a smaller room, right?
Exactly. It's like needing a bigger pump to fill up a larger swimming pool.
Right. Okay, that makes sense. What other calculations are important?
Well, another key one is figuring out the concentration of a contaminant when you're using dilution ventilation. Remember, dilution ventilation is like adding a bit of clean water to a dirty glass.
Right. It's all about diluting that concentration.
Exactly. So how do we know what the final concentration is going to be after that mixing?
Yeah, that's a good question.
Well, the guide gives us an equation for that, too.
Of course it does.
It takes into account the generation rate of that contaminant, the airflow rate, and the time. It's a little more complex than the air change calculation, but it's still manageable.
The guide actually gives us an example of this, right?
Yeah, it walks us through calculating the concentration of a contaminant in like a storage area,
Okay.
and it shows us how to plug in those values and solve for that final concentration.
So it's really helpful to see how these calculations are actually used in, real-world situations.
Absolutely. Now let's talk about a more specialized calculation, determining that rate of generation for liquid solvents. This one's particularly important for industries that use solvents, like painting, printing, and manufacturing.
So we're figuring out how fast a liquid solvent evaporates and releases those vapors into the air, right?
Exactly. And the guide, it gives us this equation that considers several factors, including the ventilation rate, the molecular weight of the solvent, the specific gravity of the solvent, and the evaporation rate.
Wow, there's a lot that goes into that calculation.
Yeah, there are a lot of factors to consider.
Why do we have to think about all those things?
Well, different solvents, they evaporate at different rates, and their vapors, they have different densities.
Oh, okay.
And they can mix with air in different ways. All of these things influence how quickly that solvent can create a hazardous atmosphere.
So it's like comparing how quickly a puddle of water evaporates on a hot day versus like how long it takes spilled oil to really disperse.
Exactly. And to build on that, let's look at another calculation determining those vapor or gaseous concentrations.
Okay, so now we're figuring out how much of a vapor or gas is actually in the air.
Right. The guide provides us with an equation that uses the partial pressure of the chemical and the barometric pressure.
Don't worry, I'm following along.
Good. So basically, by knowing the pressure of that chemical and that overall atmospheric pressure, we can determine its concentration in the air.
Okay, got it. It's like figuring out how much salt is dissolved in a glass of water based on how salty it tastes, right?
You got it. And the guide, it provides an example using a specific chemical, showing how to plug in the values and solve for that concentration. It's always good to see those equations in action.
Absolutely. It really highlights how science and engineering are applied to actually, keep us safe in the workplace and in our everyday lives.
For sure. And these calculations, they're just the tip of the iceberg when it comes to ventilation system design and management. There's a whole world of specialized knowledge and expertise involved to make sure these systems are working the way they should be.
Right, yeah.
Now, before we wrap up, I want to circle back to something you mentioned earlier, about those emerging trends in ventilation technology.
Oh, yeah, that's a good one. What are some of those innovations that are really, changing the way we think about air quality and contaminant control?
Well, one really exciting trend is the development of smart ventilation systems.
Smart ventilation systems, like a thermostat for air quality.
Exactly. These systems, they use sensors and intelligent algorithms to monitor the air quality in real time, and they can adjust those ventilation rates as needed. So instead of relying on, fixed ventilation rates, these systems can actually adapt to changing conditions.
That's amazing. It's like having a ventilation system that can think for itself.
In a way, it is. And this not only improves air quality, but it also helps us reduce energy consumption because the system only runs as much as it needs to.
So it's good for our health and the environment.
Exactly. It's a win-win situation.
What other innovations are we seeing?
Another big area is the development of advanced filtration technologies. We're seeing these new filters that can actually capture even smaller particles, including, ultrafine particles and even viruses.
Wow. That's incredible. So we're not just talking about, removing dust and fumes anymore. We're talking about actually protecting against those microscopic contaminants.
Exactly. And these advanced filters are being used everywhere now, from hospitals to homes, even in offices.
It's fascinating to see how technology is constantly evolving to make our lives safer and healthier.
It really is. And, it makes you realize how much we rely on good ventilation, often without even thinking about it.
Well, this has been an amazing journey. We've covered so much ground. We started with those basic principles of air movement, and we dove deep into the technology behind it all.
Yeah, we explored all those different types of ventilation systems, those components of local exhaust systems, even talked about air cleaning devices and how to measure and monitor these systems.
And I think we've all come away with a much deeper appreciation for the importance of ventilation and, the role that it plays in keeping us safe and healthy.
Absolutely. Ventilation, it's often overlooked, but it's truly essential for our well-being. Whether we're at work, at home, or out in public, clean air is a fundamental need.
Well said. A huge thank you to all our listeners for joining us today on this deep dive into the world of ventilation. We hope you found it informative and engaging, and as always, stay safe out there.